Hello, and welcome to Nighttime Science. Close your eyes and picture a single molecule of water. It is small, incredibly small, made of just 3 atoms bound together in a gentle bend. 2 hydrogen atoms sit at an angle to 1 oxygen atom, creating a shape that looks a bit like a wide letter V, or perhaps like Mickey Mouse's head if you let your imagination wander in the most relaxed way possible. This simple arrangement, 2 hydrogen and 1 oxygen, gives water a chemical formula you may remember from school, H2O. But this modest molecule, repeated trillions upon trillions of times, becomes the oceans, the rivers, the clouds, the ice caps, and the quiet rain that falls on a summer evening. Water is polar. The oxygen atom pulls electrons a bit more strongly than the hydrogen atoms do, creating a slight negative charge near the oxygen and a slight positive charge near each hydrogen. This imbalance is gentle, but it is enough to let water molecules hold hands, in a sense, through what scientists call hydrogen bonds. A hydrogen bond forms when the positive side of one water molecule is attracted to the negative side of another. These bonds are weak compared to the bonds that hold the atoms together inside a single molecule, but they are persistent, and they happen over and over again, creating a kind of flickering network that gives water many of its unusual properties. If you were to watch a drop of water on a calm surface, you would see it bead up rather than spread into a thin film. That is cohesion, the tendency of water molecules to stick to one another. You might also notice water climbing slightly up the sides of a narrow glass tube, defying gravity in a small, quiet way. That is adhesion, water sticking to other substances. Both cohesion and adhesion arise from hydrogen bonding, and both play roles in how water moves through soil, through the stems of plants, and across the surfaces of leaves. Now expand your view outward, away from the single molecule, away from the droplet, and imagine the entire surface of Earth as seen from space. You would see blue. So much blue. Oceans cover about 71% of our planet's surface, holding roughly 97% of all the water on Earth. The remaining 3% is fresh water, and most of that is locked away in glaciers and ice sheets near the poles, with only a small fraction flowing through rivers, sitting in lakes, soaking into groundwater, or drifting as vapor in the atmosphere. The oceans are vast reservoirs, slow and patient. They do not rush. They breathe in sunlight and breathe out heat. They absorb carbon dioxide from the air. They release water vapor that rises, cools, condenses into clouds, and eventually falls as rain or snow. Some of it back onto the ocean, some of it onto land, where it begins a long journey back to the sea. This journey is called the water cycle, and the ocean is its largest player. Scientists estimate that about 86% of global evaporation happens from the ocean surface, and about 78% of global precipitation falls back onto the ocean. The ocean is both the source and the destination, the beginning and the end, in a cycle that has been turning for billions of years. The water cycle connects the ocean to every river, every raindrop, every snowflake, and every bit of morning dew. When water evaporates from the warm surface of the tropical ocean, it carries energy with it in the form of latent heat. This energy is released when the vapor condenses into cloud droplets high in the atmosphere, warming the air and driving winds and weather patterns. When rain falls on mountains, it trickles into streams, carves valleys, nourishes forests, and eventually makes its way back to the sea, carrying dissolved minerals and nutrients. The ocean receives these gifts quietly, mixing them into its salty depths. And the oceans are salty, If you have ever tasted seawater, you know this immediately. On average, seawater contains about 35 grams of dissolved salts for every kilogram of water. Most of that salt is sodium chloride, the same substance in your kitchen salt shaker. But there are also smaller amounts of magnesium, calcium, potassium, and many other elements. These salts come from rocks on land. Rain, which is slightly acidic from dissolved carbon dioxide, weathers rocks and soil, dissolving minerals. Rivers carry these dissolved minerals to the ocean. Over geological time, the ocean has become a dilute solution of almost everything the crust of the earth has to offer. This saltiness affects the ocean in subtle but important ways. Salty water is denser than fresh water, all else being equal. Cold water is denser than warm water. So the densest water in the ocean is cold and salty, and this dense water has a tendency to sink. The interplay of temperature and salinity creates currents deep below the surface, currents that flow slowly through the dark, carrying water from the polar regions toward the equator and back again over the course of many centuries. These currents are part of the ocean's quiet heartbeat, a pulse you cannot see but that shapes the climate of the entire planet. From space, the ocean looks smooth and blue, but if you could see beneath the surface, you would find layers. Near the top, where sunlight penetrates, the water is warmer and lighter. Below that, temperature drops rapidly in a zone called the thermocline. Deeper still, the water is cold, near freezing, and nearly uniform in temperature all the way to the ocean floor. Similarly, salinity can create layers with fresher water from melting ice or heavy rainfall sitting atop saltier water, at least until winds and currents mix them together. The ocean is not a static pool. It is in constant, gentle motion. Surface currents swirl in great circular patterns called gyres, driven by the wind. Deep currents creep along the bottom, driven by differences in density. Tides rise and fall with the pull of the moon and the sun. Waves march across the surface, carrying energy from distant storms. And through it all, water evaporates, clouds form, rain falls, and the cycle continues, connecting ocean to sky, to land, and back again. In the sections that follow, we will explore these processes in more detail, moving slowly and calmly through the science of water and oceans. We will look at the strange properties that make water different from almost any other liquid. We will descend through the layers of the ocean, from the sunlit surface to the crushing pressures of the deepest trenches. We will follow ocean currents as they carry heat and nutrients around the globe. We will meet creatures that make their own light in the eternal darkness of the deep sea. We will watch particles of organic matter drift downward like snow, feeding life in the abyss and locking carbon away for centuries. We will visit coral reefs teeming with color and complexity. We will feel the rhythm of waves and tides. We will travel to the polar seas where ice forms and melts with the seasons. And we will trace the path of water as it moves from ocean to atmosphere to land and back again in an endless, quiet journey. But for now, rest easy with this thought. Water is everywhere, in you and around you, in the air you breathe, in the ground beneath your feet, and most of all in the vast, calm oceans that cover our blue planet. Water seems ordinary. It flows from your tap, fills your glass, sits quietly in lakes and seas. You might think of it as simple, unremarkable, just there. But water is strange. It behaves in ways that almost no other substance does, and these strange behaviors arise from those hydrogen bonds we mentioned earlier, those gentle attractions between molecules that form and break trillions of times every second. Let us begin with something you can feel. dip your finger into a glass of water and lift it out slowly. Notice how the water clings to your skin for a moment before dripping away. That clinging is adhesion, water sticking to your finger. Notice also how the drops that form are round and bulging, holding together until they grow heavy enough to fall. That roundness comes from cohesion, water molecules pulling on each other, trying to minimize the surface area of the drop. Both adhesion and cohesion are stronger in water than in most other liquids, and both trace back to hydrogen bonding. Hydrogen bonds form because water molecules are polar. The oxygen atom in each molecule has a partial negative charge, and the hydrogen atoms have partial positive charges. Opposite charges attract, so the positive hydrogen of one molecule draws close to the negative oxygen of another. This bond is weak, about 20 times weaker than the covalent bond that holds hydrogen and oxygen together within a single molecule, but it is persistent. Each water molecule can form up to 4 hydrogen bonds at once, 1 from each hydrogen atom and 2 toward the oxygen. In liquid water, these bonds are constantly forming and breaking as molecules jostle and tumble. But at any given moment, most molecules are bonded to several neighbors. This network of hydrogen bonds gives water a kind of internal stickiness. It takes energy to pull water molecules apart, more energy than you might expect for such a small, light molecule. This is why water has a high boiling point. Molecules similar in size to water, such as hydrogen sulfide or methane, are gases at room temperature because their molecules do not stick to each other very strongly. Water, on the other hand, remains liquid across a wide range of temperatures, from 0 degrees Celsius to 100 degrees Celsius at standard atmospheric pressure, and it stays liquid over even wider ranges at different pressures. This liquid range is crucial for life as we know it, allowing water to exist in lakes, rivers, and oceans across most of the Earth's surface. Water also has a high specific heat, meaning it takes a lot of energy to raise the temperature of water by even 1 degree. When you heat a pot of water on the stove, much of the energy you add goes into breaking hydrogen bonds rather than speeding up the molecules. This high specific heat makes water an excellent buffer against temperature changes. Large bodies of water, such as oceans and lakes, warm up slowly in summer and cool down slowly in winter, moderating the climate of nearby land. Coastal regions tend to have milder temperatures than inland areas at the same latitude, and the ocean itself changes temperature far more slowly than the atmosphere above it. Another unusual property appears when water freezes. Most substances become denser when they solidify. The molecules pack together more tightly in the solid state than in the liquid state, so a solid typically sinks in its own liquid. Water does the opposite. Ice floats. This happens because when water freezes, hydrogen bonds lock the molecules into a crystalline lattice with more space between them than in liquid water. Each molecule is hydrogen bonded to 4 neighbors in a 3-dimensional hexagonal structure, and this open arrangement makes ice about 9% less dense than liquid water. The fact that ice floats has profound consequences. In winter, when the surface of a lake or a polar sea begins to freeze, the ice forms a layer on top. This floating ice insulates the water below, slowing further freezing and allowing liquid water to persist beneath the ice. Fish and other aquatic organisms can survive the winter in the cold but unfrozen water below the ice. If ice were denser than water, it would sink as it formed, and lakes and oceans would freeze from the bottom up, likely freezing solid in many cases and making it much harder for life to survive cold seasons. In the polar oceans, Sea ice forms each winter and melts each summer in a slow, seasonal breathing. The Arctic Ocean sees its sea ice reach a minimum extent around September and a maximum around February or March. The Southern Ocean around Antarctica follows the opposite calendar, with maximum ice in the southern winter around September and minimum ice in the southern summer around February. When seawater freezes, most of the salt is excluded from the ice crystals, so the ice itself is much fresher than the surrounding seawater. The rejected salt makes the remaining liquid water saltier and therefore denser, and this denser water can sink, driving ocean circulation even in the cold, dark polar winter. Water's high surface tension is another gift of hydrogen bonding. Surface tension is the tendency of a liquid surface to act like a stretched elastic skin. It arises because molecules at the surface are pulled inward by hydrogen bonds to the molecules below them, but there are no molecules above to pull them upward. This creates a net inward pull, making the surface contract and resist being stretched. Water has one of the highest surface tensions of any liquid. This is why water forms droplets, why some insects can walk on water without sinking, and why water beads up on a freshly waxed surface. Water is also an excellent solvent, sometimes called the universal solvent, though that name is a bit of an exaggeration. Water dissolves many substances, especially those that are polar or ionic. Salt dissolves in water because the positive sodium ions and negative chloride ions are surrounded by water molecules, with the negative oxygen ends of water pointing toward the sodium and the positive hydrogen ends pointing toward the chloride. This separation and surrounding of ions is called hydration, and it allows water to carry dissolved minerals, nutrients, and gases throughout the ocean and through living organisms. All of these properties, the cohesion and adhesion, the high boiling point, the high specific heat, the lower density of ice, the high surface tension, and the solvent ability emerge from the same fundamental cause: the polarity of the water molecule and the hydrogen bonds that result. Without hydrogen bonding, water would be a gas at room temperature, ice would sink, and the climate would swing wildly between extremes. The oceans as we know them would not exist. Life, at least life built on the chemistry we are familiar with, would probably not exist either. So as you picture the vast oceans covering most of Earth, remember that they are made of this strange, cohesive, heat-absorbing, ice-floating substance. Water's unusual properties shape the way the ocean moves, the way it stores and releases heat, the way it supports life, and the way it interacts with the atmosphere and the land. These properties, gentle and persistent, are the foundation of everything else we will explore. If you were to fill a bucket with seawater and let it evaporate slowly under the sun, you would eventually be left with a white crust of salt at the bottom. This salt is not a single substance, but a mixture of many dissolved minerals that the ocean has collected over billions of years. The ocean is salty, and this saltiness is one of its defining characteristics, shaping how water moves, where it flows, and what lives within it. The average salinity of seawater is about 35 grams of dissolved salts per kilogram of water, often written as 35 parts per thousand. Another way to express this is as a salinity of 35 practical salinity units, a measurement oceanographers use that does not have traditional units but represents the same concentration. To picture this, imagine dissolving about 7 teaspoons of salt into a liter of water. That is roughly the saltiness of the open ocean. The most abundant dissolved substance in seawater is sodium chloride, common table salt, which makes up about 85% of the total dissolved solids. But seawater also contains magnesium, sulfate, calcium, potassium, bicarbonate, and trace amounts of nearly every element found in Earth's crust. These dissolved substances come primarily from the weathering of rocks on land. Rainwater, slightly acidic because it absorbs carbon dioxide from the atmosphere, falls on mountains and plains, trickles through soil, and dissolves minerals from rocks. Rivers carry this mineral-rich water to the ocean, where it mixes into the vast reservoir. Over geological time, the ocean has become a dilute solution of the continents. Salinity is not uniform across the ocean. In regions where evaporation is high and rainfall is low, such as the subtropical gyres in the middle of ocean basins, salinity tends to be higher because water evaporates and leaves the salt behind. In contrast, regions with heavy rainfall, large river inputs, or melting ice tend to have lower salinity because fresh water is added to the surface. Near the mouth of the Amazon River, for example, the ocean surface can be much fresher than average because the river pours enormous amounts of fresh water into the Atlantic. Near the poles, melting sea ice in summer adds fresh water to the surface, while the formation of sea ice in winter rejects salt and makes the surrounding water saltier. Salinity affects seawater density. All else being equal, saltier water is denser than fresher water. This makes intuitive sense. Dissolving salt in water adds mass without adding much volume, so the density increases. At a temperature of 0 degrees Celsius and a salinity of 35, seawater has a density of about 1,028 kilograms per cubic meter. For comparison, pure fresh water at the same temperature has a density of about 1,000 kilograms per cubic meter. The difference seems small, but it is enough to drive powerful currents deep in the ocean. Temperature also affects density, and in fact, temperature usually has a stronger effect than salinity in the surface ocean. Warm water is less dense than cold water because the molecules move faster and take up more space. Near the equator, where the sun heats the surface, seawater might be warm, around 25 to 30 degrees Celsius, giving it a density around 1,023 kilograms per cubic meter despite its salt content. In the polar regions, surface water might be near freezing, around -1 to 0 degrees Celsius. And if it is also salty from the rejection of salt during ice formation, it can have a density of 1,028 kilograms per cubic meter or higher. The interplay of temperature and salinity creates what oceanographers call the thermohaline circulation, a term that combines thermo for temperature and haline for salt. In the polar regions, especially in the North Atlantic near Greenland and in the Southern Ocean around Antarctica, surface water becomes very cold and often very salty. This cold, salty water is denser than the water below it, so it sinks. Once it sinks, it flows along the ocean floor, spreading slowly through the deep basins of the Atlantic, Indian, and Pacific Oceans. This deep water can take hundreds to more than 1,000 years to complete its journey, eventually upwelling in other parts of the ocean and returning to the surface. Density differences also create layers in the ocean. Near the surface, sunlight warms the water, making it lighter and causing it to float atop the colder, denser water below. This creates a relatively warm, well-mixed surface layer that can be tens to a few hundred meters deep depending on location and season. Below this surface layer is the thermocline, a zone where temperature drops rapidly with depth. In the thermocline, density increases quickly because the water is getting colder. Below the thermocline, in the deep ocean, temperature changes very little, hovering near freezing, and density remains relatively constant all the way to the ocean floor. Salinity can also create layers. Where fresh water from rain or rivers sits on top of saltier water, a halocline forms, a zone where salinity increases rapidly with depth. In some regions, the halocline and thermocline coincide, creating a pycnocline, a zone where density increases rapidly due to both temperature and salinity changes. These layers can be stable, resisting mixing, or they can be broken down by storms, winds, and currents that stir the water. The density structure of the ocean has important consequences for life and climate. The stable layering can trap nutrients in the deep water, away from the sunlit surface where phytoplankton need them. In some regions, such as the equatorial Pacific or areas near Antarctica, deep water rich in nutrients upwells to the surface, fertilizing the growth of phytoplankton and supporting rich ecosystems. In other regions, strong layering prevents this upwelling and the surface can be relatively barren. Density-driven currents also play a role in regulating Earth's climate. The sinking of dense water in the polar regions and its slow flow through the deep ocean helps transport heat from the equator toward the poles. The Gulf Stream, for example, carries warm water from the Gulf of Mexico northward along the east coast of North America, and then across the Atlantic toward Europe. Some of this warm water eventually cools, becomes denser, and sinks in the North Atlantic, contributing to the deep southward flow. This circulation moderates temperatures, keeping northwestern Europe warmer than it would otherwise be at such high latitudes. Understanding salinity and density requires patience and careful observation. Oceanographers lower instruments from ships to measure temperature, salinity, and pressure at different depths. They deploy floating sensors that drift with currents, radioing data back to satellites. They analyze water samples in laboratories, determining the precise concentrations of dissolved substances. Over decades, a picture has emerged of an ocean in constant motion, with cold, salty water sinking in the polar regions, flowing along the bottom and eventually rising again in a slow global circulation. So when you think of the ocean, do not picture a uniform, static pool. Picture instead a layered, dynamic system with warm, light water floating on cold, dense water, with rivers of fresh water diluting the surface in some places and evaporation concentrating salt in others, with currents stirring and mixing, and with the patient, invisible hand of density guiding the flow. The ocean breathes in salt from the land, exhales fresh water into the sky, and moves heat and nutrients around the planet, all shaped by the gentle mathematics of temperature, salinity, and density. Imagine standing at the edge of the ocean on a calm day, looking out at the sunlit water sparkling near the shore. The surface is bright, alive with light, warm to the touch. Now imagine descending slowly, gently down through the water column. As you sink, the light begins to fade. The water grows cooler, the pressure increases, the world changes layer by layer until you reach a place of total darkness and crushing weight, a place as different from the sunlit surface as the surface of another planet. The ocean is not a uniform column of water. It is divided into distinct zones, each defined by how much sunlight penetrates, how cold the water is, and how much pressure bears down from above. These zones stack atop one another like the layers of the atmosphere, each hosting different communities of life and different physical conditions. The shallowest zone, the one you see when you look at the ocean, is called the epipelagic zone, or sometimes the sunlight zone. It extends from the surface down to about 200 meters, or roughly 650 feet. Within this zone, sunlight is abundant enough for photosynthesis to occur. Phytoplankton, microscopic plant-like organisms, drift in the currents, using sunlight and dissolved carbon dioxide to create organic matter and release oxygen. These phytoplankton form the base of the ocean food web, feeding zooplankton, which in turn feed fish, which feed larger fish and marine mammals. The epipelagic zone is the most familiar part of the ocean, the part where coral reefs grow, where dolphins leap, where most commercial fishing takes place. Below the epipelagic zone lies the mesopelagic zone, also known as the twilight zone, stretching from about 200 meters down to 1,000 meters, or roughly 3,300 feet. Here, sunlight is dim, a faint blue glow filtering down from above, but it is not enough for photosynthesis. The temperature drops significantly in this zone, often falling from the warm surface temperatures to just a few degrees above freezing. Many animals in the mesopelagic zone migrate vertically, rising toward the surface at night to feed in the richer waters above, then descending during the day to avoid predators. This daily migration involving billions of small fish, squid, and crustaceans is one of the largest movements of biomass on Earth. Deeper still is the bathypelagic zone or midnight zone, extending from about 1,000 meters down to 4,000 meters, roughly 13,000 feet. No sunlight reaches this depth. The water is perpetually dark, cold, hovering near 2 to 4 degrees Celsius. Pressure is immense, hundreds of times greater than at the surface. Life here is sparse compared to the surface, but it exists, adapted to the darkness and the cold. Many creatures in the bathypelagic zone produce their own light through bioluminescence, using chemical reactions to create glowing spots and patterns on their bodies. Below the bathypelagic zone is the abyssopelagic zone, stretching from 4,000 meters down to 6,000 meters, or nearly 20,000 feet. This is the abyssal plain, the vast flat expanse of the deep ocean floor. The temperature is near freezing, the pressure enormous, the darkness absolute. The ocean floor here is covered with fine sediment, the accumulated remains of countless tiny organisms that have drifted down from the surface over millions of years. Life is slow and patient, consisting of scavengers, deposit feeders, and microbes that process the organic matter that settles from above. The deepest zone is the Hadal zone, found in ocean trenches deeper than 6,000 meters. The word Hadal comes from Hades, the ancient Greek underworld, and it is fitting. The Hadal zone includes the deepest known point in the ocean, the Challenger Deep in the Mariana Trench, which reaches down nearly 11,000 meters, or about 36,000 feet. At such depths, the pressure is staggering, more than 1,000 times atmospheric pressure at sea level. Yet even here, life persists. Strange fish, amphipods, and microbes that have adapted to conditions that would instantly crush most surface organisms. Pressure increases steadily as you descend through these zones. At the surface, the pressure is 1 atmosphere, the weight of the column of air above you. For every 10 meters, or about 33 feet, you descend into the ocean, the pressure increases by approximately 1 atmosphere. This happens because water is much denser than air, so even a relatively short column of water weighs a great deal. At 100 meters depth, the pressure is about 11 atmospheres, 10 from the water and 1 from the air above. At 1,000 meters, the pressure is about 101 atmospheres. At the bottom of the Challenger Deep, the pressure reaches approximately 1,100 atmospheres, or more than 16,000 pounds per square inch. To put this in perspective, if you took an empty sealed container to the deep ocean, the pressure would crush it flat. If you took a styrofoam cup to great depth and brought it back, it would be compressed to a fraction of its original size. Human bodies, being mostly water, are less compressible, but the pressure would still be lethal without protection. Deep-sea submersibles must be built with thick, strong hulls to resist the crushing force of the water. Yet life has found ways to survive these pressures. Deep-sea organisms do not have air-filled spaces in their bodies that would collapse under pressure. Their cells are filled with water and specialized molecules that help maintain function under high pressure. Some deep-sea fish have soft, gelatinous bodies with no swim bladders. Some have proteins and cell membranes that remain flexible and functional even when compressed. Evolution has shaped these creatures over millions of years, slowly refining adaptations that allow them to thrive in a world of darkness and pressure. The ocean floor itself is not flat and featureless. It has mountains, valleys, plains, and trenches much like the land surface, only hidden beneath kilometers of water. The continental shelf is the shallow, gently sloping extension of the continents, typically less than 200 meters deep, where the epipelagic zone meets the seafloor. Beyond the shelf is the continental slope, a steeper descent down to the deep ocean basins. The abyssal plains are the vast, flat regions of the deep ocean floor, interrupted here and there by underwater mountains called seamounts, volcanic ridges, and deep trenches. Mid-ocean ridges are underwater mountain ranges where tectonic plates are pulling apart and new oceanic crust is forming. These ridges can rise 2 to 3 kilometers above the surrounding seafloor and run for thousands of kilometers across the ocean basins. Near the ridges, hydrothermal vents can form, cracks in the seafloor where superheated water, rich in minerals and chemicals, spews into the cold ocean. These vents support unique ecosystems based not on sunlight and photosynthesis, but on chemosynthesis, where bacteria use the chemicals from the vents as an energy source. Trenches, on the other hand, are the deepest parts of the ocean, formed where one tectonic plate is being forced beneath another in a process called subduction. The Mariana Trench, the Tonga Trench, the Philippine Trench, and others plunge to depths of 8,000 to 11,000 meters. These are among the most extreme environments on Earth. Yet scientific expeditions have found life even in the deepest trenches. Life that has adapted to the cold, the darkness, and the pressure. As you imagine descending through these zones, picture the gradual changes. The warm, bright surface gives way to the dim twilight of the mesopelagic. The twilight fades to the absolute blackness of the bathypelagic. The water grows colder and colder until it hovers just above freezing. The pressure builds layer by layer, atmosphere by atmosphere, until it becomes almost unimaginable. And yet in each zone, life has found a way, quietly, patiently adapted to conditions that seem hostile but that have been stable for millions of years. The vertical structure of the ocean, these layers of light and darkness, warmth and cold, low pressure and high pressure, shapes everything that happens in the sea. It determines where phytoplankton can grow, where fish can feed, where nutrients are stored, and where carbon is sequestered. Understanding these zones is essential to understanding the ocean as a whole. And as we continue our journey through ocean science, we will return to these layers again and again. The ocean never stops moving. Even in the calmest bay on the stillest day, water is flowing beneath the surface, driven by forces you cannot see. Some of this motion is fast and near the surface, pushed by the wind. Some of it is slow and deep, driven by differences in temperature and salinity that make water heavy enough to sink and patient enough to creep along the ocean floor for centuries. Surface currents are the most visible part of ocean circulation. They are driven primarily by the wind. As the wind blows across the ocean surface, it drags the water along, creating currents that can flow for thousands of kilometers. In each major ocean basin, surface currents form large circular patterns called gyres. In the northern hemisphere, these gyres rotate clockwise. In the southern hemisphere, they rotate counterclockwise. The motion is gentle but persistent, shaped by the rotation of the Earth, a phenomenon called the Coriolis effect, which deflects moving water to the right in the northern hemisphere and to the left in the southern hemisphere. The Gulf Stream is one of the most famous surface currents. It begins in the Gulf of Mexico, flows northward along the east coast of the United States, and then curves eastward across the Atlantic toward Europe. The Gulf Stream carries warm water from the tropics toward higher latitudes, transporting an enormous amount of heat. This warmth moderates the climate of northwestern Europe, making places like Ireland and the United Kingdom milder than they would otherwise be at such northern latitudes. Without the Gulf Stream, winters in these regions would be far colder. But surface currents are only part of the story. Below the wind-driven surface layer lies a different kind of circulation, slower and deeper, driven not by wind but by differences in water density. This is the thermohaline circulation, sometimes called the global ocean conveyor belt. The word thermohaline combines thermo, meaning temperature, and haline, meaning salt, because both temperature and salinity determine the density of seawater. The thermohaline circulation begins in the polar regions, particularly in the North Atlantic near Greenland and Iceland, and in the Southern Ocean around Antarctica. In these cold places, seawater at the surface loses heat to the frigid air and cools down. In the North Atlantic, evaporation and the formation of sea ice can also increase the salinity of the surface water, because when ice forms, it excludes most of the salt, leaving the remaining liquid water saltier. Cold, salty water is very dense, denser than the water below it, so it sinks. This sinking is slow and gentle, but it is powerful. The dense water descends into the deep ocean, sometimes reaching depths of 2 to 3 kilometers or more. Once it sinks, it begins a long journey along the ocean floor. In the Atlantic, the deep water flows southward, hugging the western boundary of the basin, eventually reaching the Southern Ocean. There, it mixes with other deep waters and continues eastward, flowing into the Indian Ocean and the Pacific Ocean. In the deep ocean, the water moves very slowly, perhaps only a few centimeters per second, a pace you could barely perceive if you were swimming alongside it. But over decades and centuries, this slow flow carries water halfway around the world. Eventually, the deep water begins to rise, upwelling toward the surface in regions of the Pacific and Indian Oceans and in parts of the Southern Ocean. This upwelling can occur gradually over large areas or more rapidly in specific regions where winds and currents favor it. Once the water returns to the surface, it warms, its density decreases, and it joins the surface currents, flowing back toward the Atlantic in great loops. The entire journey from sinking in the North Atlantic to upwelling in the Pacific and returning to the Atlantic can take roughly 1,000 years. 1,000 years for a single molecule of water to complete the circuit, drifting through the dark, cold depths, rising again into the light, warming, and eventually sinking once more. This global conveyor belt does more than just move water. It moves heat. Surface currents carry warm water from the equator toward the poles, releasing heat into the atmosphere as they go. Deep currents carry cold water from the poles toward the equator, where it eventually rises and absorbs heat from the sun. This redistribution of heat helps moderate Earth's climate, preventing the equator from becoming unbearably hot and the poles from becoming even colder. The thermohaline circulation also moves nutrients and dissolved gases. Deep water, isolated from the atmosphere for centuries, can accumulate nutrients from the slow decay of organic matter that sinks from above. When this nutrient-rich water upwells to the surface, it can fertilize the growth of phytoplankton, creating productive regions of the ocean that support abundant fisheries. The waters off the coast of Peru, for example, benefit from upwelling driven by winds and currents, and they are among the most productive fishing grounds in the world. The strength and pattern of the thermohaline circulation can change over time. During past ice ages, changes in ocean circulation may have contributed to rapid climate shifts. There is concern that human-caused climate change could alter the circulation in the future. As the planet warms, ice sheets in Greenland and Antarctica may melt more rapidly, adding fresh water to the ocean surface in polar regions. This added fresh water would make the surface water less dense, potentially reducing the rate at which it sinks and weakening the thermohaline circulation. A weaker circulation could in turn affect climate patterns around the world, though the exact consequences are still being studied. For now, the ocean continues its slow, patient breathing, the surface warming and the depths cooling, water sinking in the cold polar night and rising again in distant seas warmed by the sun. Currents swirl and flow, carrying heat, nutrients, and life across the globe. The ocean is not a static reservoir, but a dynamic, interconnected system, and the currents are its circulatory system, its pulse moving unseen beneath the waves. Water does not stay in one place. It moves constantly from ocean to sky to land and back again in a cycle that has been repeating for billions of years. This movement is called the water cycle or the hydrologic cycle, and it links the ocean, the atmosphere, the land, the ice, and all living things in an endless exchange. The ocean is the heart of the water cycle. It holds about 97% of all the water on Earth, far more than all the rivers, lakes, ice caps, and groundwater combined. Each day, the sun shines down on the ocean surface, warming the water and providing energy for evaporation. Water molecules at the surface absorb energy, break free from their hydrogen bonds, and escape into the air as water vapor. This process is called evaporation, and the ocean contributes an enormous amount of it, roughly 86% of all the water that evaporates from Earth's surface each year. As water evaporates, it carries energy with it in the form of latent heat. Latent heat is the energy required to change water from liquid to vapor without changing its temperature. When water evaporates from the warm tropical ocean, it cools the surface slightly, taking heat energy into the atmosphere. This energy is stored in the water vapor, invisible and patient, until the vapor rises, cools, and condenses into tiny droplets to form clouds. When condensation occurs, the stored latent heat is released, warming the surrounding air. This release of heat drives much of the atmospheric circulation, powering winds, storms, and weather patterns. Once water vapor has risen into the atmosphere and condensed into clouds, it can travel long distances carried by the wind. Eventually, the droplets grow heavy enough to fall as precipitation, rain, snow, sleet, or hail. About 78% of global precipitation falls back onto the ocean. The rest falls on land. Precipitation that falls on land begins a different journey. Some of it soaks into the soil, infiltrating downward to become groundwater. Groundwater can flow slowly underground, emerging in springs, seeping into streams, or being drawn up by plant roots. Some precipitation runs over the surface as runoff, flowing into creeks, rivers, and lakes. Rivers carry this water along with dissolved minerals and sediment back toward the ocean. Some precipitation falls as snow on mountains and ice caps, where it can remain frozen for years, decades, or even millennia before melting and continuing its journey. But eventually, almost all of the water that falls on land makes its way back to the ocean. Rivers deliver it directly. Groundwater seeps into coastal aquifers and then into the sea. Glaciers calve icebergs that drift and melt. Even water taken up by plants is eventually released back into the atmosphere through transpiration, the process by which plants release water vapor from their leaves, and that vapor joins the atmospheric flow, condenses, falls again, and flows back to the ocean. The water cycle is not a simple loop with a single path. It is a complex network with many branches and timescales. A water molecule might evaporate from the Pacific Ocean, condense into a cloud, fall as rain on a forest in the Amazon, be absorbed by a tree, transpired back into the air, fall again as rain on a river, flow to the Atlantic Ocean, evaporate again, fall as snow on Greenland, be locked in ice for 1,000 years, melt, flow into the ocean and begin again. The journey is unpredictable, driven by winds, currents, temperature differences, and chance. The ocean's role in the water cycle also makes it a crucial part of the climate system. The ocean absorbs solar energy, stores it as heat, and releases it slowly over time. Water vapor carried from the ocean into the atmosphere is a greenhouse gas, trapping heat and warming the planet. The movement of water from ocean to atmosphere to land redistributes both water and energy, shaping regional climates. Monsoons, for example, are driven in part by seasonal differences in heating between land and ocean, which create pressure differences that draw moist air from the ocean over the land, bringing heavy rains. The water cycle also transports nutrients and chemicals. Rain can carry nitrogen from the atmosphere to the soil, fertilizing plants. Rivers carry dissolved minerals, organic matter, and pollutants from the land to the ocean. The ocean, in turn, releases gases like carbon dioxide and oxygen into the atmosphere through exchange at the surface. Human activity has altered the water cycle in subtle and not so subtle ways. Dams change the timing and amount of river flow. Irrigation withdraws groundwater and surface water, sometimes faster than it can be replenished. Deforestation reduces transpiration and increases runoff. Urbanization creates impermeable surfaces that prevent infiltration and speed runoff into rivers. Climate change, driven by the buildup of greenhouse gases, is altering precipitation patterns, increasing evaporation in some regions and intensifying storms in others. Yet through all of these changes, the basic cycle continues. Water evaporates, condenses, falls, flows, and evaporates again. The ocean remains the largest reservoir, the great collector of rivers, the source of most evaporation, the destination of most precipitation. It is patient and vast, absorbing changes and buffering extremes, maintaining a rhythm that has persisted through ice ages and warm periods, through the rise and fall of continents, through the slow march of geological time. So when you watch rain fall, or see a river flow, or feel the mist rising from the ocean on a warm day, remember that you are watching the water cycle in action, the endless journey of water from sea to sky to land and back, a journey that connects every part of the Earth system in a slow, quiet dance. Stand on a beach for a few hours and you will notice the ocean rising and falling. The water creeps up the sand, reaching a high point, then retreats, leaving behind wet sand and stranded shells. This gentle, rhythmic rising and falling is the tide, one of the most predictable and ancient motions of the ocean. Tides are caused primarily by the gravitational pull of the moon. The moon orbits Earth, and as it does, its gravity pulls on everything on our planet, including the water in the oceans. Gravity decreases with distance, so the side of Earth closest to the moon feels a stronger pull than the center of the Earth, and the center feels a stronger pull than the side farthest from the moon. This difference in gravitational force, called a tidal force, stretches the ocean slightly, creating a bulge of water on the side facing the moon and another bulge on the opposite side. As Earth rotates beneath these bulges, different locations on the planet pass through the high points and low points of the tidal bulge. Most coastlines experience 2 high tides and 2 low tides each day, corresponding to the 2 bulges. The time between high tides is roughly 12 hours and 25 minutes, a bit longer than half a day, because the moon is also orbiting Earth in the same direction that Earth is rotating. So it takes a little extra time for a given point on Earth to catch up to the moon's position. The sun also exerts a gravitational pull on Earth's oceans, but its effect is smaller than the moon's, even though the sun is far more massive. This is because the sun is also much farther away, and tidal forces depend on the difference in gravitational pull across the diameter of Earth, which decreases rapidly with distance. The sun's tidal force is about 46% as strong as the moon's. When the sun, Earth, and moon are aligned, either during a new moon or a full moon, the tidal forces of the sun and moon add together, creating larger tidal bulges and therefore higher high tides and lower low tides. These are called spring tides, though the name has nothing to do with the season. When the sun and moon are at right angles to each other during the first and third quarters of the moon, their tidal forces partially cancel, creating smaller tidal bulges and therefore smaller differences between high and low tides. These are called neap tides. The range of the tides, the difference in height between high tide and low tide, varies greatly depending on location. In the open ocean, tidal range is typically less than a meter. But near coastlines, especially in bays and estuaries with the right shape, tides can be amplified. The Bay of Fundy between New Brunswick and Nova Scotia in Canada has the highest tides in the world, with a range that can exceed 16 meters or more than 50 feet. As the tidal bulge enters the funnel-shaped bay, the water is squeezed and forced upward, creating these dramatic tides. Tides have a profound effect on coastal ecosystems. Intertidal zones, the areas between high and low tide, are alternately submerged and exposed, creating a challenging environment where organisms must cope with changing water levels, temperature fluctuations, drying out, and the pounding of waves. Yet these zones are often rich with life. Barnacles, mussels, crabs, sea stars, anemones, seaweeds, and many others, all adapted to survive the rhythm of the tides. While tides are driven by gravity and are predictable over long time scales, waves are driven by wind and can be chaotic and variable. Waves form when wind blows across the surface of the ocean, transferring energy from the air to the water. The size of the waves depends on the wind speed, how long the wind blows, and the fetch, which is the distance over which the wind blows across the water. When you watch a wave, it appears that water is moving forward, rolling across the ocean surface. But in reality, most of the water is not traveling with the wave. Instead, the wave is a moving pattern of energy. Individual water particles move in roughly circular orbits as the wave passes. At the surface, a particle moves forward as the crest approaches, upward as the crest passes, backward as the trough approaches, and downward as the trough passes, returning nearly to its starting position. The deeper you go, the smaller these circular orbits become, and below a depth of about half the wavelength, the water is barely affected by the wave. When waves travel from the open ocean toward the shore, they begin to feel the bottom as the water becomes shallow. The circular orbits of water particles become compressed into ellipses, and the wave slows down. As the wave slows, its wavelength decreases, but its energy remains the same, so the wave height increases. Eventually, the wave becomes too steep and unstable, and it breaks, releasing its energy in a tumble of white foam. This breaking of waves on the shore is one of the most iconic sights and sounds of the ocean, a constant reminder of the energy that travels across the water. Waves can travel enormous distances. Swells, long-period waves generated by distant storms, can cross entire ocean basins, traveling thousands of kilometers before finally breaking on a distant shore. Surfers seek out these swells using the energy that began as wind in a storm far out at sea. Tides and waves are different kinds of motion driven by different forces, but both are part of the rhythm of the ocean. Tides are slow, predictable, driven by the gravitational dance of Earth, Moon, and Sun. Waves are fast, variable, driven by the restless wind. Together they shape coastlines, mix the surface water, bring nutrients and oxygen to coastal ecosystems, and create the dynamic, ever-changing boundary between ocean and land. Pressure is the weight of everything above you, pressing down. When you stand on the surface of the earth, you feel the weight of the atmosphere, a column of air stretching from your head to the edge of space. This atmospheric pressure is about 14.7 pounds per square inch, or roughly 1 kilogram per square centimeter. Though you do not notice it because your body is built to withstand it, and because the pressure inside your body balances the pressure outside. In the ocean, pressure increases much more rapidly with depth than it does in the atmosphere with altitude, because water is about 800 times denser than air. Every 10 meters you descend, roughly 33 feet, adds another atmosphere of pressure. At 10 meters depth, the pressure is 2 atmospheres, one from the water and one from the air above. At 100 meters, the pressure is about 11 atmospheres. At 1,000 meters, about 101 atmospheres. At the average ocean depth of about 3,700 meters, the pressure is roughly 380 atmospheres. In the deepest trenches, pressure becomes almost unimaginable. The Challenger Deep in the Mariana Trench, at a depth of nearly 11,000 meters, experiences a pressure of more than 1,100 atmospheres, equivalent to over 16,000 pounds per square inch, or about 8 tons per square inch. If you could somehow place a 1-inch square tile at that depth, the water pressing on it would weigh as much as a small car. This immense pressure affects everything. Air-filled spaces collapse. Foam compresses to a tiny fraction of its original volume. Fragile structures crumble. The human body, if exposed to such pressure without protection, would not be crushed in the dramatic sense often depicted in movies, because our bodies are mostly water and water is nearly incompressible. But the pressure would force gases dissolved in body fluids to dissolve further or compress, and it would make normal biological processes impossible. We are not built for the deep ocean, yet life has adapted. Deep-sea organisms do not have air-filled swim bladders like many surface fish, because such bladders would collapse under the pressure. Instead, deep-sea fish often have soft, gelatinous bodies, or they use oils and other substances that are less compressible than air to maintain buoyancy. Their cells contain specialized proteins and molecules, such as trimethylamine N-oxide, that help stabilize proteins and membranes under high pressure. These adaptations have evolved over millions of years, allowing life to colonize even the deepest parts of the ocean. Pressure also affects the properties of water itself. At very high pressures, water becomes slightly more dense than it is at the surface, though the change is small. The speed of sound in water increases with pressure, which is why sonar signals travel faster in the deep ocean than near the surface. Chemical reactions can proceed differently under high pressure, and some minerals and compounds that are stable at the surface become unstable in the deep, or vice versa. Human exploration of the deep ocean has required remarkable engineering. Submersibles that carry people to the deep sea must have thick, strong hulls to resist the pressure. The first manned descent to the Challenger Deep was made in 1960 by Jacques Picard and Don Walsh in the bathyscaphe Trieste, a vessel with a thick steel sphere for the crew and a large float filled with gasoline, which is less dense than water and helped provide buoyancy. More recently, filmmaker James Cameron descended to the Challenger Deep in a specially designed submersible, and unmanned robotic vehicles have explored many of the ocean's deepest places. Pressure in the ocean also influences where and how organisms live. The rapid increase in pressure with depth creates distinct habitats. Organisms adapted to shallow water cannot survive in the deep, and deep-sea organisms brought to the surface often do not survive the decrease in pressure. This creates a kind of vertical zonation, with different communities at different depths, each adapted to the specific conditions of pressure, temperature, light, and food availability. The weight of water pressing down through kilometers of ocean is a constant, invisible force shaping the deep sea. It is part of the reason the deep ocean is so different from the surface, so alien, so difficult for humans to reach. But it is also a testament to the adaptability of life, which has found ways to thrive under conditions that seem to us utterly hostile. In the deep ocean, where sunlight never reaches, darkness is absolute. There is no day, no night, no seasons of light and shadow, only an endless, lightless void. Yet this darkness is not empty. It is filled with life, and much of that life glows. Bioluminescence is the production of light by living organisms through chemical reactions. It is remarkably common in the ocean, especially in the deep sea. Scientists estimate that around 76% of animals in the open ocean produce light in some form. This makes bioluminescence one of the most widespread adaptations in the marine environment. The chemistry of bioluminescence is elegant. It typically involves a light-emitting molecule called luciferin and an enzyme called luciferase. When luciferin reacts with oxygen in the presence of luciferase, it produces light. The reaction is efficient, producing light with very little heat, unlike the glowing filament of a light bulb. Different organisms use different types of luciferin and luciferase, and they produce light of different colors, though blue and green are most common because these wavelengths travel farthest in seawater. Some organisms produce light themselves using specialized light-producing cells called photophores. Others harbor symbiotic bacteria in special organs, and the bacteria produce the light. The relationship is mutualistic. The bacteria gain a safe place to live and access to nutrients, and the host gains the ability to produce light. Bioluminescence serves many functions in the deep sea. One of the most common is counterillumination, a form of camouflage. Many deep-sea fish and squid have light-producing organs on their undersides. When viewed from below, these organisms would normally appear as dark silhouettes against the faint light filtering down from above. By producing light on their undersides that matches the intensity and color of the downwelling light, they can erase their silhouette and become nearly invisible to predators or prey looking up from below. Another function is attracting prey. The anglerfish is perhaps the most famous example. It has a long, modified spine extending from its head, tipped with a glowing lure. In the darkness, the glow attracts smaller fish and crustaceans which come to investigate, only to be snapped up by the anglerfish's large jaws. The light in the lure is produced by symbiotic bacteria living in the tip. Bioluminescence can also be used for communication. Some species use specific light patterns to recognize members of their own species to attract mates or to coordinate group behavior. Flashlight fish, for example, have large light organs under their eyes filled with glowing bacteria. They can cover and uncover these organs to create flashing signals. Defense is another use. When threatened, some organisms produce a burst of bright light, startling or confusing a predator. Others release glowing chemicals into the water, creating a luminous cloud that can distract or illuminate the predator, making it visible to its own predators. Some deep-sea squid eject a cloud of glowing mucus instead of ink, creating a glowing decoy that the predator attacks while the squid escapes into the darkness. The distribution of bioluminescence varies with depth. In the mesopelagic zone, the twilight zone, bioluminescence is extremely common, perhaps because this is a zone where there is still a faint glow of sunlight from above, making silhouette concealment important. Deeper, in the bathypelagic and abyssopelagic zones, bioluminescence remains common, though the functions shift more toward attracting prey and communication. On the ocean floor, bioluminescence can be seen as well. Some bottom-dwelling fish, shrimp, and other creatures glow. Even some bacteria in the sediment produce light, creating faint ghostly glows on the seafloor. The study of bioluminescence has practical applications beyond understanding ocean life. The enzymes and molecules involved in bioluminescence have been used in medical and biological research as markers and tracers. Green fluorescent protein, originally isolated from a jellyfish, glows green when exposed to blue light and has become an essential tool in cell biology, allowing researchers to track specific proteins and processes within living cells. But perhaps the most remarkable thing about bioluminescence is what it represents. Life adapting to the absence of sunlight by creating its own light. In the deepest, darkest parts of the ocean, where you might expect only emptiness, there is instead a quiet, glowing world, full of creatures producing cold, chemical light for hunting, hiding, signaling, and surviving. It is a reminder that life is resourceful, persistent, and endlessly creative. In the sunlit surface waters of the ocean, microscopic phytoplankton drift in the currents, using sunlight and dissolved carbon dioxide to build their bodies through photosynthesis. They are the base of the ocean food web, consumed by tiny zooplankton, which are in turn consumed by fish, and so on up the chain. But not all of this organic matter is eaten. Some of it dies, some is expelled as waste, and some is shed as mucus, molts, or other detritus. All of this material begins to sink. As it sinks, it encounters other sinking particles, and they stick together, forming larger aggregates. These aggregates, along with fecal pellets from zooplankton and other organic debris, drift slowly downward through the water column, creating what oceanographers call marine snow. Marine snow is not snow in the familiar sense. It does not fall from clouds, and it is not made of ice. It is a continuous, gentle rain of organic particles falling from the sunlit surface into the deep ocean. If you could see it, it would look like soft, fluffy flakes drifting slowly downward, some small, some large, some moving quickly, some caught in eddies and taking a slower path. Most marine snow is consumed or broken apart before it reaches the ocean floor. Bacteria colonize the particles, breaking them down and consuming the organic matter. Zooplankton feed on the larger aggregates. Fish and other midwater organisms intercept particles as they fall. But despite all this consumption, a fraction of the organic matter, perhaps around 15% of what is produced at the surface, makes it to the deep ocean. This sinking of organic matter is part of the ocean's biological pump, a process that moves carbon from the surface to the deep. Phytoplankton at the surface absorb carbon dioxide from the atmosphere and seawater, fixing it into organic molecules. When these organisms die and sink or are eaten and their remains sink, the carbon is transported downward. In the deep ocean, the carbon can remain sequestered for hundreds or even thousands of years, isolated from the atmosphere until deep currents eventually bring the water back to the surface. The efficiency and strength of the biological pump can vary depending on conditions. Storms can enhance the formation and export of marine snow by disturbing the water column and aggregating particles. Blooms of phytoplankton triggered by an influx of nutrients can produce large amounts of organic matter that sinks rapidly. In some regions, such as the Southern Ocean, the biological pump is particularly strong because cold, nutrient-rich waters support high productivity. Marine snow also provides food for organisms living in the deep sea, far from sunlight and photosynthesis. Deep-sea creatures depend on this rain of organic matter from above as their primary source of energy. Without marine snow, the deep ocean would be a barren desert, unable to support the life that inhabits it. The study of marine snow and the biological pump is important for understanding the global carbon cycle and climate. The ocean absorbs a significant fraction of the carbon dioxide that humans emit into the atmosphere, and much of this carbon is eventually transported to the deep ocean by the biological pump. Understanding how this process works and how it might change in the future is crucial for predicting how the ocean will respond to increasing atmospheric carbon dioxide levels. So the next time you think of snow, think also of the ocean's silent snowfall, the gentle drift of particles from the sunlit surface to the dark depths, carrying carbon, nutrients, and energy, feeding life in the abyss, and shaping the chemistry of the sea and the air above. Coral reefs are among the most vibrant and diverse ecosystems on Earth, rivaling tropical rainforests in the sheer number of species they support. Built by tiny animals called corals, these underwater structures create complex three-dimensional habitats full of crevices, overhangs, tunnels, and platforms. Within this architecture, thousands of species find food, shelter, and places to reproduce. Corals themselves are colonies of small, soft-bodied animals called polyps, related to jellyfish and sea anemones. Each polyp secretes a hard calcium carbonate skeleton, and over time, as generation after generation of polyps live and die, their skeletons accumulate, forming the massive reef structure. Some reefs have been growing for thousands of years, building upward and outward as sea level rises and the reef keeps pace. Most reef-building corals live in a symbiotic relationship with microscopic algae called zooxanthellae, which live inside the coral tissues. These algae use sunlight to photosynthesize, producing sugars and other nutrients that the coral polyps use for energy. In return, the algae receive a safe place to live and access to nutrients from the coral's waste products. This partnership allows corals to thrive in nutrient-poor tropical waters because they can supplement their diet of plankton with energy from the algae. Coral reefs support an extraordinary diversity of life. Fish of every shape, size, and color dart among the coral branches. Invertebrates such as shrimp, crabs, lobsters, sea stars, sea urchins, sponges, and mollusks hide in crevices and forage on the reef. Sea turtles and rays glide over the reef while sharks patrol the outer edges. Scientists estimate that coral reefs, which cover less than 1% of the ocean floor, are home to about 25% of all marine species. The Coral Triangle, a region in the western Pacific Ocean encompassing parts of Indonesia, Malaysia, the Philippines, Papua New Guinea, Timor-Leste, and the Solomon Islands, is the global center of marine biodiversity. This region contains more coral species, more fish species, and more invertebrate species than any other marine area on Earth. The reasons for this extraordinary diversity are complex, involving the region's position at the crossroads of ocean currents, its geological history, and the variety of habitats it provides. Coral reefs perform many ecological functions. They provide habitat and food for countless species. They protect coastlines from storm waves and erosion by absorbing wave energy. They support fisheries that feed millions of people. They attract tourists, generating income for coastal communities. They are also sources of new medicines, as reef organisms produce unique chemical compounds for defense and communication, some of which have potential pharmaceutical applications. But coral reefs are fragile. They are sensitive to changes in water temperature, and warming ocean waters can cause corals to expel their symbiotic algae in a process called coral bleaching. Without the algae, the coral loses its color and its primary source of energy, and if conditions do not improve, the coral can die. Pollution, overfishing, destructive fishing practices, coastal development, and ocean acidification also threaten reefs around the world. Despite these threats, coral reefs continue to thrive in many places, testaments to the resilience and adaptability of life. They remind us that complexity and diversity can arise in the most unexpected places, built grain by grain, polyp by polyp, over long stretches of time. We have traveled together through the science of water and oceans, moving slowly and calmly from the smallest molecule to the largest currents, from the bright surface to the crushing depths, from the quiet rain falling to the ancient ice forming and melting at the poles. Along the way, we have learned that water is strange and wonderful, that the ocean is layered and dynamic, that currents move heat and nutrients across the globe, that life glows in the darkness, that particles drift like snow through the depths, and that reefs teem with color and complexity. All of these phenomena are connected. The hydrogen bonds that make water sticky also make ice float, which insulates polar seas and allows life to survive the winter. The salinity and temperature of seawater determine its density, which drives the slow, deep currents that carry water around the world for centuries. The water cycle links ocean, atmosphere, and land in an endless exchange of moisture and energy. Tides and waves shape coastlines and mix the surface waters. Pressure increases with depth, creating distinct habitats and shaping the adaptations of deep-sea life. Bioluminescence lights the darkness where sunlight cannot reach. Marine snow carries carbon and nutrients from the surface to the depths. Coral reefs build complex structures that support a quarter of all marine species. Understanding these connections can feel calming, like learning the rhythms of a vast, patient system that has been operating for billions of years. The ocean is not chaotic or random. It follows patterns shaped by gravity, sunlight, the rotation of the earth, the chemistry of water, and the interactions of countless organisms. These patterns are gentle, persistent, and deeply interwoven. As you drift towards sleep, perhaps you can picture the ocean as a whole, the sunlight warming the surface, the evaporation rising into clouds, the rain falling, the rivers flowing back to the sea. Picture the tides rising and falling with the moon, the waves carrying energy across the water, the currents swirling in great loops. Picture the deep, cold water sinking at the poles and creeping along the ocean floor, rising again centuries later. Picture the lights flickering in the darkness, the particles drifting downward, the reefs growing grain by grain. The ocean covers most of our planet, holds most of its water, drives much of its weather, and supports an incredible diversity of life. It is patient and powerful, absorbing heat and carbon, buffering changes, connecting distant places. It is worth understanding, worth protecting, worth contemplating as you fall asleep, letting its slow rhythms match your breathing. Its vast scale put your worries in perspective. If you enjoyed this journey through the gentle science of water and oceans, consider liking this video and subscribing to the Nighttime Science channel for more quiet, calming explorations of the natural world. There is always more to learn, more connections to discover, more beauty in the details of how our planet works.